All right, hi everyone. So this is a quick video explanation of the photoelectric effect question that I gave to you guys in the class. Now, I hope you guys remember the question and the options which were there. So let's start the solution by first understanding what this I versus V graph is. The I on the y-axis represents the photocurrent and the V on the x-axis represents the potential difference that you have applied. So I hope you remember the setup of photoelectric effect, right? There was a metal plate on which radiation will strike and then electrons will get ejected and get collected on the collector plate, and then a circuit gets completed in which we can notice or read the values of photocurrent that is there. And we also have a battery connected so as to accelerate or stop the electrons, right? Now, if the in the graph on the y-axis, if you will notice, the positive potential difference that will be applied will be called as accelerating potential difference, because it will help in increasing the kinetic energy of the ejected electrons, whereas the negative potential difference that would be applied, that will be called as the stopping potential difference, because it will help, it will be, the direction will be in such a manner that will reduce the kinetic energy, right? So based on this understanding, now you can understand two important features in this graph. Let's first discuss this point on the x-axis. Now, as you can notice, this is a point where the it's a stopping potential where the photocurrent has become zero, right? So this is the potential difference that is applied, the negative potential difference that needs to be applied to stop any electrons from reaching the collector plate. Hence, no photocurrent, right? And how is it calculated? You remember from our class discussions that the magnitude of the stopping potential that needs to be applied should be equal to the kinetic energy of the electrons, the maximum kinetic energy of the electrons. Now, if it is in the units of EV, then you can write the value of stopping potential, that same value, in terms of volts. We did this calculation, the units part as well. Now, imagine we are reducing this stopping potential. That means we are allowing these electrons to reach the other side. And as a result, what we start observing is a photocurrent in the circuit. So you can see that the photocurrent starts to increase. Now, why is it that the photocurrent is increasing? Because, as I said last time also, that when photons strike, electrons get ejected. Not all the electrons have same kinetic energy. Some have low, some have high, right? And some lose energy because of collisions and are not able to reach the other side. So by applying this potential difference, right, and in fact making it an accelerating potential difference, we are making sure that these ejected electrons are able to reach the detector plate. And beyond a certain point, wherein we have accelerated the electrons, we have provided them the energy to reach the other side, we find that the current has saturated. And why did this current saturate? This saturation current corresponds to the possible electrons that were ejected by the possible photons, right? So we were striking the photons and say almost all of the electrons were getting ejected and reaching the other side. Then increasing the potential difference will not increase the current anymore. So we call this as a saturation current. So these are the two important features of this graph that will help us answer this question. Now, let's come to each of these plates one by one. So there was plate P, Q, and R with different stopping potentials, and all the three plates were being exposed by a beam containing these three kinds of radiations. Right? Plate Q is also exposed to these three kind of radiation. Plate Q is also exposed to these three kind of radiations, as well as plate R. Now, noticing the energy of photons in these radiations, we understand that the 550 nanometer radiation has a photon of energy 2.25 eV, which is greater than the stopping potential of the plate, and hence the electrons can be ejected. Right? They can have, right? It's a can condition. They can have a maximum kinetic energy of 0.25 eV, which will be 2.25 minus 2 eV. However, in case of plate Q, the energy of the 550 nanometer photon is lesser than the work function, and hence that radiation will not be able to eject the electrons. And same goes for plate R, that the 550 nanometer radiation will not be able to eject the electron because the energy of the photon is less than the work function. Now let's talk about the 450 nanometer radiation. So we calculate the energy of the 450 nanometer radiation. The energy of the photon comes out to be 2.75 eV, which again will be able to eject the electron from plate P with a max kinetic energy of 0.75 eV. Right? This corresponds to 2.75 minus 2. Right? That is the energy of the photons or the electrons that can be ejected by the 450 nanometer radiation in case of plate P. Now, in case of plate Q, right, you focus on the plate Q, the 450 nanometer radiation will be able to eject electrons because the energy of photons is greater than its work function, which was 2.5 eV. So in this case, yes, electron ejection does happen, and their kinetic energy, the maximum kinetic energy, can be 2.75 minus 2.5, which is 0.25 eV. In case of plate R, which has a higher work function, that is 3 eV, even the 450 nanometer radiation is not able to eject electrons. As you can see that the energy of the 450 nanometer photon is 2.75 eV, which is less than the work function. And lastly, we talk about the 350 nanometer radiation. That 350 nanometer radiation will be able to eject electrons in the similar way that we have thought about the previous radiations. It will be able to eject electrons from plate P, Q, as well as from plate R. However, the kinetic energy of the electrons will be different because of their different work functions. Right? In the plate P, the kinetic energy of the electrons, maximum kinetic energy, will be 1.55 minus, 3.55 minus 2 eV, which comes out to be 1.55 eV. In case of plate Q, right, the energy of photon will be 3.55 eV minus the work function, which was 2.5 eV. So the Ke max comes out to be 1.05 eV. And in case of plate R, the energy of photon 3.55 eV was able to eject electrons, and 3.5 minus the work function, which was 3 eV, we got the kinetic energy to be 0.55 eV. So based on this analysis, we can first comment on the photocurrent. Right? In case of plate P, as you can notice, all the three radiations were able to eject electrons, and as a result, more photons were able to eject more electrons, and the photocurrent will be highest. As compared to plate Q, where only two radiations were able to eject electrons, as compared to plate R, where only one radiation was able to eject electrons. So only one radiation ke photons were able to eject electron, and hence the photocurrent here is less. Now, why was I able to compare the photocurrent? Because it was given in the question that the intensity of all three radiations is same, right? So what do I mean by that? Like equal intensity, that means all these radiation had same, you can say, count of photons. So for example, plate P, right, which was struck by these three radiations, say 100, 100 and 100 photons, 100 each were coming from these three types of radiations, then all of them were able to eject electrons. So it has got maximum electrons getting ejected. And subsequently, you can now figure out that for plate Q and R, the number of electrons ejected would be lesser. So this is about the photocurrent. Secondly, when we think about the stopping potential, like the stopping potential, as I said in the previous definition also, it is the potential difference that we need to apply to ensure that the fastest electrons or the electron with the maximum kinetic energy is stopped. Now, in case of plate P, all the three radiations are ejecting electrons, and their Ke max is also different, and we focus on the one which is the highest, right? So the 350 nanometer is able to eject the electrons with maximum kinetic energy, which is 1.55 eV. So you'd want to apply a potential difference that can stop that electron, and hence the stopping potential will be minus 1.55 volts. Right? If the stopping potential is able to stop this electron, which is this much kinetic energy, then all these rest of the electrons will also get stopped. Similarly, when we focus on plate Q, right, when we look at the kinetic energy of the electrons ejected, we find that it was 1.05 eV, which was the maximum kinetic energy of the ejected electrons that we are getting. So we need to apply a potential difference of 1.05 volts. And similarly for plate R, it is only this 350 nanometer radiation which is able to eject electrons with kinetic energy 0.55 eV, and hence the stopping potential of minus 0.55 volts is required. So in terms of the magnitude of the stopping potential, if I was to compare P, Q and R, I will find that magnitude of stopping potential required for plate P is more than Q, more than plate R. And now this can help us conclude that option A is the correct answer. As you can notice, the stopping potential of plate P, Q and R is in the correct order. That plate P, in terms of magnitude, please notice that plate P requires more stopping potential than Q than R. And in terms of the saturation current also, you can see that the current in case of plate P is more than Q than R, because here more photons were able to eject electrons as compared to plate Q, as compared to plate R. All right, so I hope this was informative enough for you and detailed enough for you to be able to grasp this question. It was a good question, difficult question. It was in fact asked in one of the previous JEE advanced examinations. I don't remember the year, but yes, it was a good question. We could have solved it much faster also, but that requires you to be more experienced with the problem solving in photoelectric effect, and you could have not detailed this much, but still get the answer. All right, thank you guys.